Welcome back to the deep dive. Today we're pulling back the curtain on something that I think a lot of us just take for granted.
Oh, absolutely.
You know the feeling, you're in the zone, you've got your headphones on, coffee in hand, you're writing code, you hit that build button, and magic happens. A binary just comes out the other end. But today we are talking about the invisible backbone that makes that magic possible. It's a tool that has been around for decades, yet I feel like very few people actually, understand it. We're talking about Make.
It is the absolute classic. And honestly, despite being a tool from, what, the 70s?
Yeah, 1976, I think.
Right. It is still often the most misunderstood piece of software in the modern developer's toolkit. The source text we are looking at today, Managing Projects with GNU Make, 3rd edition by Robert Mecklenburg, has this great phrase for it. It calls Make the servant that takes over the enterprise.
I love that phrasing. It's so evocative. He calls it an enticing servant.
It really captures the psychology of using it. It's almost literary in how it describes a piece of software.
Right. Because it starts as this underappreciated supplicant. You throw it a few odd jobs like, oh, compile this one file, or, move this binary to the bin folder. And then gradually, almost without you noticing,
Peeks over everything.
exactly, it takes over the entire enterprise. It becomes the absolute center of your project's universe.
That is the perfect description of the life cycle of a makefile. It starts simple. You just want to save yourself typing out a long GCC command every single time. But before you know it, it's managing your unit testing, your documentation generation, deployment scripts, container builds. I mean, it really does become the operational definition of your project. If it's not in the makefile, does it even exist?
Probably not.
Yeah.
So let's go back to the beginning before we get into all that complexity. Why do we even need this? I mean, I could just write a shell script to compile my code. I could write a batch file. Why bother with this specific slightly weird syntax and all these rules?
You absolutely could use a shell script. And for a tiny, hello world project, maybe that works perfectly fine. But think about the classic frustration of the edit, compile, debug cycle. You're working on a massive project. You modify a function in one little utility file. You run the build script. And you wait.
And you wait.
And you wait, because the script is just blindly recompiling everything.
Right. Every single file, even the ones that haven't changed in months.
Exactly. A shell script is procedural. It says, do step A, then do step B, then do step C. It doesn't care if step A is actually necessary right now. It just does it. But there's a much worse scenario.
Oh, I know this one. You try to get smart.
Yes. You try to manually run just the compiler for the one file you changed. You run the code and
the bug is still there.
The bug is still there. You spend an hour debugging code that isn't even running because you forgot to recompile it or you forgot to relink the executable.
I have absolutely been there. It is maddening.
That is the specific acute pain point that Make solves. It moves us away from that procedural mindset of do this, then this, and forces us into a declarative mindset.
Declarative.
Yeah.
That's a really key term here for you listening. So instead of telling the computer what to do step by step, you're telling it about the relationship.
Precisely. You tell Make, here are the relationship between my files, here is the dependency graph. You literally declare this executable depends on these object files, and these object files depend on these source files. And then you step back.
You let it do the thinking.
You let Make figure out the minimum amount of work needed to bring everything up to date based on that graph.
It's almost like you're defining the ideal state of the world, and Make is the engine that enforces that state. But how does it actually know? Like, is it reading the code? Is it doing some deep semantic analysis of the C syntax to see what changed?
No, and that's honestly the genius of it. It's much, much simpler. It is fundamentally a timestamp comparison engine.
Timestamps. That's it.
That's it. It looks at the timestamp of the source file and compares it to the timestamp of the output file. If the source is newer than the output is considered stale. It needs to be rebuilt. If the output is newer, Make assumes everything is fine and just does nothing.
It sounds so simple, almost primitive. But that simple logic is what allows it to scale to massive, sprawling projects like the Linux kernel.
Yeah.
If you have to rebuild the whole kernel every time you tweaked one audio driver, you'd never get anything done.
Exactly. It turns an hour-long build process into a 5-second incremental update.
So our mission today for this deep dive is to move past just writing a simple build script. We want to really understand Make not just as a task runner, but as a fully featured programming language for build automation. Because when you get down to it, it is a language, isn't it?
Oh, it absolutely is. It
Okay.
has variables, conditionals, functions, and even metaprogramming capabilities, which we'll definitely get into. We want to get you to the point where you see the matrix, so to speak.
Let's start with the atoms of this universe then, the rule. When I open up a Makefile and look at it, what am I actually seeing?
You are seeing a collection of rules, and every rule has three distinct non-negotiable parts. You have the target, the prerequisites, and the commands.
Okay, break that anatomy down for us.
Sure. The target is the thing you want to create. Usually it's a file, let's say countwords.o, an object file.
Got it.
The prerequisites, which are sometimes called dependencies, are the files needed to create that target. So that would be your countwords.c source file and maybe a header file. And finally, the commands are the actual shell instructions to do the physical work, like running gcc-c countwords.c.
So the logic flows like this. To get target A, I need prerequisites B and C. If B or C have a newer timestamp than A, run the commands.
Yes, that is the core loop. And here's where we hit the most infamous quirk in the history of software build tools, the syntax for those commands.
Oh boy, I know exactly where you're going, the tab character.
The tab character. The line containing the commands must begin with a literal tab character. Not 4 spaces, not 8 spaces, a tab.
I feel like every single person who has ever written a Makefile has been burned by this at least once. You copy and paste a snippet from a blog post. Your code editor helpfully converts it to spaces because, hey, spaces are modern and Make just completely explodes.
It gives you that wonderfully cryptic error commence before first target, or sometimes missing separator. It's a total rite of passage. And it's tricky because if you accidentally put a tab at the start of a line that isn't a command, Make might actually try to execute it as a command later and fail weirdly.
Why? I have to ask, why hasn't this been fixed in 40 years?
It's purely historical. Stuart Feldman, the guy who wrote the original Make back in 1976, has actually admitted it was a rush job. He used a tab character because it was really easy to parse with the tools he had. By the time he realized it was a terrible idea, he already had a dozen users, which back then was a huge user base, and he didn't want to break backward compatibility. So here we are, decades later, still furiously hitting the tab key.
That is incredible. A design decision from the 70s dictating the formatting of modern software. So, to everyone listening, watch your white space. Now, let's talk about how these rules connect, because a single rule is fine, but the real power comes from chaining them, right?
Exactly. That's the dependency graph in action. Let's look at the example Mecklenburg uses in the book. We have a program that counts words. The final executable is called countwords. That executable depends on object files, let's say countwords.o and lexer.o.
Okay, so Make checks the executable against the timestamps of those object files.
Right. But Make doesn't just stop there. It looks at lexer.o. It searches its internal database for a rule where lexer.o is the target. It finds one that says lexer.o depends on lexer.c.
Right, it's walking backward down the tree.
But wait, in this specific example, lexer.c isn't written by hand. It's generated from a flex file, lexer.l. So Make finds yet another rule. A lexer.c depends on lexer.l.
So we had a distinct chain. The .l file generates a .c file, which compiles to a .o file, which links to the executable.
Exactly. When you ask Make to build the executable, it walks all the way down that chain recursively before it does any work. It checks the .l file first. If that's changed, it knows it needs to run flex to rebuild the .c file. Since the .c file is now newly generated, its timestamp just updated, so it realizes it needs to rebuild the .o file. And since the .o file is new, it finally relinks the executable.
It just ripples all the way back up the chain.
It ripples up. But here's the real beauty of it. If you only change the main countwords.c file, Make sees that the lexer.l file hasn't changed. It compares the timestamps and sees lexer.c is already newer than lexer.l, so it skips that flex generation step entirely. It only executes what is strictly necessary.
Now, what happens to those intermediate files, like lexer.c in that example? Just a stepping stone. Does Make keep it around, just cluttering up your source directory?
Generally, no. Make is pretty smart about intermediate files. If it generates a file purely to get to the next step in a chain, like that generated lexer.c, it will automatically delete it once the whole build is done to keep your source tree clean.
That's nice, but what if I actually need to see it? Maybe the flex generator's producing buggy C code, and I need to open it up and debug it.
You can tell it to stop deleting things. You can use special built-in targets like .precious or .secondary. If you list a file as a prerequisite of .precious, Make says, okay, I will keep this file around permanently, even if I only created it just for this specific build chain.
That seems like an absolute lifesaver for debugging code generators. Okay, so we have the basic structure down, target, prerequisite, command, and we chain them together. But if I have a project with 50 source files and I have to write 50 specific rules with hard-coded file names, that makefile is going to be a total nightmare to maintain.
It would be completely unmanageable. You spend more time fixing the make file than writing your actual application code. We need abstractions. We need variables.
Absolutely. And this is where Make starts to feel much more like a real programming language. But reading through the source material, I realized Make variables are weird. They come in two very distinct flavors.
They do, and confusing these two is probably the #1 source of bugs for intermediate users. You have simply expanded variables and recursively expanded variables.
Let's unpack those. Simply expanded uses the colon equals operator, right?
Correct. This behaves like variables in almost every other programming language you're used to, like Python or C. When make reads the line with colon equals, it expands the value right then and there.
So if I say cc colon equals gcc at the top of the file, cc is evaluated as gcc immediately.
Right. It's a static snapshot.
Right.
If you use other variables inside that definition, it grabs their values at that exact moment in time. It freezes the state.
Okay, that seems standard enough. What's the other one? The recursively expanded variable.
That one uses just the plain equal sign, and this is the lazy variable. It doesn't expand when the line is read. It just stores the raw text of whatever you assign to it. It only expands when the variable is actually explicitly used later in a rule.
Why does that distinction matter, practically speaking? It sounds like a minor technicality.
Oh, it matters a lot. It allows for some very powerful tricks. For example, you can define variables out of order. You can define A equals $B at the top of your file and define B all the way at the bottom. Since A isn't expanded until it's used, which is probably inside a rule execution at the very end, it picks up the value of B perfectly correctly.
Ah, I see. It's like a promise to go find the value later. But I imagine that lazy evaluation can get you into deep trouble.
It certainly can. The classic trap here is infinite recursion. Imagine you want to add a flag to your compiler options. You might intuitively try to write cflegs equals $cflegs-O for optimization.
Oh, I see exactly what's going to happen. When it finally tries to expand cflegs, it sees $cflegs, which looks up cflegs, which sees $cflegs, and you just blow up the stack.
Exactly. Thankfully, modern Make will actually catch that and yell at you with a recursive variable reference error. If you want to append to a variable safely, you shouldn't use the equals sign. You should use the append operator, which is plus equals.
Plus equals, that seems much, much safer.
It is. Plus equals knows how to handle the self-reference safely. It's absolutely crucial when you're building up a list of flags or source files across multiple different files included in your project.
And there's one more assignment operator I saw in the notes. Question mark equals.
That is the conditional assignment. It basically says, set this variable to this value, but only if it doesn't already have a value assigned to it.
That sounds perfect for setting defaults.
It is exactly for defaults. It's designed for environment overrides. You can say out2put_dir question mark equals dot/build in your makefile. Then, if a user just types make normally, the output goes to that build folder. But if they run make out2put_dir equals /tmp/, make sees that the variable was already injected from the command line, so it ignores your default inside the file completely. It empowers the user to override your settings.
That is really handy for CI/CD pipelines too. Okay, moving on to one of the things that makes Make, well, terse. Automatic variables.
Yes.
These are those magic symbols like $at and $.
Yes, the infamous line noise aspect of Make. People look at a Makefile and they just see $signs and random punctuation and their eyes glaze over. But these symbols are incredibly important. The entire goal here is don't repeat yourself. You don't want to physically type the file name countwords.o twice inside the single rule for countwords.o.
Because if you rename the file later, you have to remember to change it in two places, which is a recipe for a broken build. So run us through the big ones.
The most common one is $at. That stands for the target file name. So if your rule starts with myprogram : inside that rule's commands, $at expands exactly to the string myprogram.
Okay, simple enough to remember. At equals target, where you are aiming at.
Then you have $. That represents the first prerequisite. Usually in a compile step, that's your source file. So in a rule compiling foo.c to foo.o, $, evaluates to foo.c. Think of it visually as an arrow pointing from the source file toward the target.
That mental image really helps, actually. And what if I have a list of prerequisites? Like I'm linking a bunch of object files together to make an executable so there isn't just one source file.
Then you use $caret. That stands for all prerequisites. It gives you the whole list, space separated, with any duplicates automatically removed.
Got it. And there's one more really interesting one mentioned in the book. Dollar question mark.
Dollar question mark is really cool. It expands to only the prerequisites that are newer than the target.
Oh, that sounds very specific. When would you practically use that?
It's mostly used for updating archives or static libraries. Imagine you have a library file, a data file, that contains 50 compiled object files. You don't want to re-add all 50 to the archive every single time you change just one C file. Dollar question mark lets you write a command that says, take only the specific files that changed and update just those in the archive. It is a massive performance win for library maintenance.
That makes a lot of sense. So we have variables, we have automatic variables. Now, let's talk about avoiding boilerplate entirely. We mentioned earlier that writing 50 explicit rules is bad. How do we tell Make a general, overarching concept?
That is where pattern rules come in. This is how you tell Make, here is a general recipe for turning one type of file into another type of file.
The syntax is usually something like %.o colon %.c, right?
Exactly. The percent sign is a wildcard. It essentially says, to make any file ending in .o, look for a prerequisite file with the exact same stem, the same name part, but ending in .c.
And then you use those automatic variables we just talked about in the actual command.
Right. You'd write the command underneath as $cc-c $(-o $at. That perfectly translates to run the C compiler on the source file to create the target file. You write that tiny 3-line block once, and it seamlessly applies to every single C file in your project, whether you have 5 files or 5,000.
That is so much cleaner. It reduces the Makefile from hundreds of repetitive lines to just a few core concepts.
And here's the real kicker. Make actually comes preloaded with a massive database of these rules out of the box. It already knows how to turn .c into .o. It knows how to turn .yacc files into .c. It knows about Fortran, Pascal, text.
Wait, really? So I don't even have to write that pattern rule for C files?
Often, no. If you just list the object files you want as prerequisites for your final program, Make will search its implicit database. It'll say, I need foo.o. I don't see an explicit rule for it in the file. Let me check my built-ins. Do I see a foo.c lying around on the disk? Yes. Great, I already know exactly what compiler command to run.
That's incredibly convenient, but also kind of invisible. It feels a bit like magic happening behind the scenes. How do I know what rules it's actually using? Or what rules even exist in that database?
You can actually ask Make to dump its entire brain. If you run make-p or make-print database, it will print out thousands of lines showing every single variable and rule it currently knows, including all those built-ins.
Wow, that is a lot of output to sift through.
It is huge, but it's invaluable when you're debugging why Make is doing something you didn't expect. Sometimes it picks a weird built-in rule for a file type you didn't even know existed just because the extensions matched.
Now, you mentioned something in the notes called static pattern rules. How is that different from the normal pattern rule we just discussed?
A normal pattern rule applies to everything globally. Any .o file it can find anywhere it tries to build, sometimes that's just too broad. Maybe you have 2 distinct sets of object files in your project that need to be compiled with completely different compiler flags. A static pattern rule lets you say, apply this pattern rule, but only to this specific, explicitly defined list of files. It's a hybrid. It gives you the brevity of wildcard patterns, but the strict control of explicit rules.
Okay, let's zoom out a bit. Real software projects aren't just a flat folder of files. We have complex directory structures. We have src, include bin lib folders. How does Make handle finding files when they're scattered in different places?
This is a very common pain point for people scaling up their Make files. By default, Make only looks in the current working directory. If you want it to look elsewhere, you have to explicitly tell it. There are 2 main ways to do this: vpath and vpath.
What's the difference there? One is uppercase and one is lowercase.
It's more than just the case formatting. vpath, all caps, is the blunt instrument. It's a variable. You set it to a colon-separated list of directories, and Make will search all of those directories for literally any file it needs that it can't find locally.
Oh, like a path variable in your bash shell.
Exactly like that, but sometimes that's way too aggressive. Maybe you have a file with the exact same name in 2 different folders, say one is a generated source file and one is a backup header, and Make grabs the wrong one because of the search order.
So vpath is a hammer.
Right. It lacks precision. Vpath, all lowercase, is the scalpel. It's a directive, not a standard variable. You can use it to map specific file patterns to specific directories. You can say, search the sysrc directory, but only for files matching the pattern %.c, or search the include directory, but only for %.h files.
That is much, much safer. It prevents those weird wrong file bugs that take days to track down. Speaking of useful features, we absolutely need to talk about phony targets. We touched on this briefly with the concept of a clean command.
Right. This is a concept that always trips up beginners. A target like clean isn't an actual file you want to build. You aren't trying to generate a document named clean on your hard drive. You just want a convenient way to run a shell command to delete your build artifacts.
Make fundamentally assumes everything is a file. So what happens if I accidentally create a text file named clean in my project directory?
That is exactly the risk. If a file named clean literally exists on disk, Make looks at the rule for the clean target in your file. It usually has no prerequisites listed. So Make checks the file clean on disk, sees it exists, and says, hey, the target clean is already up to date. I don't need to do anything.
Disaster. It just quietly exits and won't run your cleanup command at all.
Exactly. So to fix this, you use the special built-in target.fhony. You list clean as a prerequisite of .fhony. This explicitly tells Make, ignore the file system for this specific target. This isn't a real file. Always run the commands associated with it.
It's basically you saying to the tool, I know what I'm doing. Stop checking timestamps. Just run the script.
Exactly. It's standard practice for targets like all, clean, install, test, really anything that isn't producing a physical file on disk.
Okay, now we're getting into the deep end of the pool. We need to talk about one of the trickiest problems in C and C++ build systems, dependency generation.
This is the classic, I changed a header file, but the code didn't recompile, and now everything is broken problem.
Right. Let's walk the listener through why that happens. Make knows that a .o object file depends on a .c source file. But inside that .c file, there's an include statement for header.h. If I go in and modify header.h, the .c file itself hasn't technically changed its timestamp, so Make thinks everything is completely fine. But the compiled code is fundamentally different because the header it pulls in changed.
And if you don't recompile that object file, you might have a struct that changed its memory size, or a function signature that swapped arguments, and you get a bizarre segmentation fault at runtime. It's a complete nightmare to debug.
So the naive fix for this is to just manually list every single header file dependency in the make file, like main.o depends on main.c, main.h, utils.h, network.h.
Which is humanly impossible to maintain for large projects.
Yeah.
You'll eventually forget one, and you'll introduce subtle build bugs. We absolutely need automation here.
So how do we actually solve this? The book mentions a really cool feature to handle it.
We use a feature of the C compiler itself. Most C compilers like GCC or Clang have a specific flag, -m. When you run the compiler with -m, instead of actually compiling the code, it just scans the source, parses all the include statements, and outputs a list of dependencies formatted specifically in Make syntax.
Wait, it literally writes the make rule for you.
It writes the rule for you. It outputs plain text that says file.o::file.cheader.h, another .h.
That's incredibly clever.
Yeah.
So you generate these little text files, usually with a .d extension for dependency.
Right, .d files. But here's the trick. You have these .d files sitting on your disk. How do you get Make to actually read them and care about them? You use the include directive inside your Make file.
Just like a hash include in C code.
Very similar concept. You write include and then a list of your .d files. Make will literally read the text of those files and seamlessly add those rules to its internal dependency graph.
But wait, I see a major chicken-egg problem here. What if the .d file doesn't exist yet? Like the very first time I clone the repo and run the build, the include directive would fail because the file isn't there.
This is where Make gets really clever. The big twist, if you will. Make treats files listed in an include directive as targets themselves.
Whoa, explain that. How does that work?
When Make starts up, it reads the Make file top to bottom. It hits the include line. If the .d file is missing or its timestamp is out of date compared to the C file, Make literally pauses the parsing phase. It says, I need to include this file, but it's not ready. Do I have a rule somewhere to build it?
And you, the developer, provide a pattern rule to build a .d file from a .c file using that GCC-m flag.
Exactly. So Make runs that specific rule, generates the .d file, and then this is the truly magic part. It restarts itself entirely. It throws away its current state and reloads the Make file from scratch, now successfully including the brand new dependency file it just created.
That is incredibly meta. It builds instructions before it builds the project.
It is, and it solves that niggling problem of header updates completely. It ensures your dependency graph is always 100% accurate, automatically every single time. You never have to worry about missing a header dependency ever again.
That is so impressive. It really shows how Make is vastly more than just a dumb script runner. It's a highly dynamic engine.
And if you want to talk about dynamic, we have to talk about functions.
Yes, Make has
Yeah.
built-in functions. I feel like people forget this. They think it's just variables and rules.
It actually has a whole standard library of functions. It has powerful string manipulation functions like subst for substitute and patsubst for pattern substitute. You use these constantly to transform lists of files, like take this list of 50 source files and dynamically change the extension from .c to .o to generate my target list.
Right, like $parentheses patsubs %.c %.o $sources.
Exactly. Then you have list filtering functions like filter and filter out. You have a massive list of all files in a directory, but you only want the C files, you use filter %.c. If you want to deliberately remove the headers from a list, you use filter out %.h.
And then there's the shell function. This one seems incredibly powerful, but also fairly dangerous.
It is. The shell function lets you run an arbitrary external command in your terminal, capture the standard output, and bring it directly into a make variable. Like running shell date to get the exact build timestamp, or shell find .-name wildcard.c to dynamically find all your source files instead of hard coding them.
Why do you say it's dangerous, though?
Performance. Remember those recursively expanded variables we talked about earlier? The lazy ones with just the equal sign?
The ones that evaluate later, yes.
If you assign a shell function to a recursive variable, Make will literally execute that shell command every single time that variable is referenced anywhere in your rules.
Oh, wow. So if I have files equals shell find, and I reference files 100 times in various different rules.
You spawn the find process 100 separate times during one build. Your build slows to an absolute crawl, and you're sitting there wondering why Make is so slow. So for shell functions, you almost universally want to use the immediate assignment, the colon equals, to run it exactly once and cache the result.
That is a pro tip right there.
Yeah.
Now, what about user-defined functions? Can we write our own custom logic?
Yes, you can. You can use the define directive to create what are essentially multi-line macros or canned sequences, and you can actually pass arguments to them dynamically using the call function.
Like call my function, arg1, arg2.
Right. And inside the function definition itself, you refer to those arguments as $1, $2, and so on. It's structurally simple, but it allows you to beautifully encapsulate complex logic, like maybe a highly complicated deployment command sequence involving SSH and SCP, so you don't have to repeat that awful block of bash in every single deployment rule.
And then there's the big one, the brain melter, as the source notes aptly call it, evil.
Ah, evil. This is Make's ultimate meta-programming facility. Evil allows you to generate makefile syntax dynamically on the fly as a text string and have immediately parse it and inject it into the graph as if you had typed it directly in the file.
Okay, give me a concrete scenario for this. Why would I do that? That sounds overly complicated for a normal project.
It is complicated, but it becomes necessary at scale. Imagine you have a massive repository with a list of 20 distinct microprograms you need to build. They all follow a very similar rule structure, but maybe the target names are derived from their parent folder names in some weird non-standard way that a simple pattern rule just cannot express.
Okay, I can picture that.
You could write 20 brittle explicit rules by hand. Or you could use a for-loop function to iterate over the list of directories, dynamically construct a custom rule string for each program using string manipulation functions, and pass that fully formed string to evil.
So you are writing make script that writes more make script.
You are. It dynamically expands into rules that Mix then instantly adds to its dependency graph. It's incredibly powerful for generating large, complex build systems without boilerplate, but debugging it is challenging, to say the least.
I can imagine. Because if you get a syntax error, the compiler is pointing to an error in code that doesn't physically exist in the text file you're looking at.
Exactly. The dreaded missing separator error often points to an evil call gone wrong where you accidentally forgot to inject a literal tab character into the generated string.
Let's pivot to something a bit more grounded.
Yeah.
Libraries. Building C libraries is a super common task. Archives, data files.
Right. An archive is fundamentally just a bag of object files zipped up together. The naive way to build one is to just delete the old library entirely and re-add every single object file. But that's incredibly slow.
Because you're rebuilding a massive archive, even if only one tiny file inside it changed.
Correct. The better, much more idiomatic way is to use Make's built-in lib parenthesis member syntax. You can actually tell Make that a prerequisite is a specific internal member inside the archive rather than a standalone file.
And if you combine that with that $? Automatic variable we talked about.
Exactly. You pass only the specific changed object files to the R command, which is the archive utility. It patches the archive in place, inserting only the new objects. It is vastly faster.
Now, what about circular dependencies in libraries? I've seen this before in legacy codebases. Library A needs library B, but library B calls a helper function located in library A. The linker just completely freaks out.
Yes, the linker processes libraries strictly in order, linearly. It does not look backward. So if you pass -LA -LB when it processes A, it notes some undefined symbols. Then it checks B, resolves them, but then it might find new undefined symbols in B that are actually located back in A, but it has already closed file A. It absolutely won't go back to look.
So what's the fix in the makefile?
The brute force, but standard fix is to literally repeat the library on the command line. -A -LB -LB -LA.
That feels so dirty.
It does feel dirty, but it works. And Make actually provides a specific automatic variable for this edge case. $+ It is exactly like $, which lists all prerequisites, but it intentionally keeps the duplicates. Normally, Make strips duplicates out to save time, but here you actually mathematically need them to satisfy the linear linker.
Fascinating. It really does handle all the weird edge cases of C compilation. Let's talk about the execution environment itself, the shell.
By default, Make uses /bin/shesh to execute all your commands. This is strictly for maximum portability across different Unix systems. But /bin/shesh can actually be different underlying shells on different operating systems.
On Ubuntu Linux, it's usually dash,
Right.
right? Or bash on older systems.
Right, it's usually a symlink to dash or bash. But strictly speaking, it's only guaranteed to be a basic POSEX compliant shell. If you are writing a makefile for a closed, controlled environment, like just your company's internal build servers, and you want to use fancy bash-specific features like pipe fail or process substitution, you should explicitly set shell equals /bin/bash at the top of your makefile.
They don't rely on whatever the user's default environment happens to be.
Exactly. Otherwise, your complex build script might work perfectly on your machine, but fail completely on your colleague's laptop because they use Zesh or some other shell that handles string escaping slightly differently.
That makes total sense. And we talked earlier about command modifiers, like using the @ symbol at the start of a command to magically silence its output so you don't print a huge GCC string. What about the hyphen modifier?
The hyphen tells Make to explicitly ignore any errors returned by that specific command.
Why would you ever want to ignore errors?
Yeah.
Make is supposed to stop dead if something breaks, right?
Usually, yes, you want it to halt. But consider a clean target. You run arm**.o. If there are currently no object files in the directory, the arm command returns a non-zero error code because it couldn't find anything to delete. You really don't want your entire build process to crash and report failure just because there was nothing left to clean up.
Yeah.
So you write -arm**.oo.
Ah, that makes perfect sense. It's basically a try this, but honestly, don't worry about it if it fails command.
Just be very careful not to overuse it. You definitely don't want to accidentally ignore actual compilation errors.
Definitely not. Now let's talk about debugging. We've written this incredibly complex makefile with evil and recursive variables and static patterns, and it's just not working. How do we figure out what's actually going on under the hood?
Debugging declarative logic is inherently hard because you can't really step through it line by line with debugger like you would a standard C program. But you do have some very good tools built in.
You mentioned the info and warning functions earlier.
Yes, you can surgically insert $warning $variable right into the middle of your makefile. When Make parses that line, it evaluates the variable and prints the value straight to the console. It's basically print to debugging for makefiles.
What if I want to just see what Make thinks it should do without actually letting it run any destructive commands?
That is the -n flag or -- just print. It does a full dry run. It resolves the whole graph and prints the exact shell commands it would execute, but skips running them. It is incredibly useful for verifying your logic before you accidentally delete your entire source tree with a bad clean rule.
And if I want to see the final result of all those implicit built-in rules and dynamic pattern matches,
that's the -p flag we discussed, print database. It dumps the entire internal state. It shows you exactly which explicit or implicit rule Make ultimately decided to select for a specific target. If your custom pattern rule isn't firing, -p will let you see exactly what rule took precedence over it.
I read you can even write your own custom trace functions, right?
You can. If you get really advanced, you can wrap your functional logic in a user-defined wrapper that automatically prints entering function X and leaving function X using the warning function. It takes some initial boilerplate to set up, but for massive enterprise-level builds, it's an absolute lifesaver for tracking down exactly where a variable is getting mangled.
So we've covered a massive amount of ground today. We've done from writing simple manual rules to automatic dependency generation, all the way to string evaluating metaprogramming. It's clear that Make is a total beast of a tool.
It really is. It's a highly specialized language.
Yeah.
And like mastering any language, there's a clear hierarchy of knowledge you progress through.
Right. Level 1 is just writing simple, hard-coded rules, target, prerequisite, command, just getting it working.
And then level 2 is introducing variables, generalizing your script so it's maintainable. Level 3 is utilizing patterns to completely eliminate repetitive boilerplate.
And level 4 is wielding functions and evil. True dynamic code generation.
That's when you finally become the build wizard of your team.
I really love that quote from the source text again. The Make utility is an enticing servant. Make starts out as the underappreciated supplicant and then gradually takes over the entire enterprise.
It's so true. It evolves to become the definitive knowledge base for how your software is actually constructed. It documents the complex relationships and architectural decisions that otherwise only exist inside the senior developer's head.
So here's my final challenge to you, the listener. Go look at your current project's build script. Whether it's an old makefile or maybe you're using something newer that was heavily inspired by it, look for that underlying dependency graph. Ask yourself, do I actually understand the fundamental relationships here, or am I just blindly running a procedure? And what if that dependency graph concept isn't just for compiling files? What if it applies to your team's workflow or your organizational structure? Where else are you waiting on a procedural step when you could be declaring relationships and letting the system optimize itself?
Find the invisible backbone in your own work.
Exactly. Thanks for diving deep with us today. We'll see you on the next one.
Happy building!